Hi, folks, welcome back. So, lately, as people have been using agents, especially coding agents and building systems, the question has always been how do you keep climbing up the ladder of abstraction? So, if you are manually having to do something with your agent, how do you get yourself out of the loop? How do you get the humans out of the agentic loops so that the agents themselves can do the work? And Karpathy recently put out this really interesting example of making the leap up the ladder of abstraction. You've probably heard of this. AutoResearch is a repo where he purely automatically trains an LLM. This is a small LLM, but what he is showing is that starting with a simple training program. So he has a train.py, bunch of Python code that trains an LLM, and then he has an agent simply try out lots of experiments. And the goal of all these experiments is to optimize one variable. This is the metric he's looking at, validation bits per byte, which is basically a measure of how well the model performs on a held out data set. But the point is that he's doing all this purely automatically, and you can see how that metric is getting optimized over time as this auto research loop does more and more experiments. And the point he was trying to make is that this is typically what a machine learning researcher would be doing manually. He'd set off a training run, look at the metrics, then make some changes to his training logic, and then repeat. And he showed that you can completely automate this cycle with a model. Now, the crucial thing here is that you have one very unambiguous, very clear metric to optimize. And today I want to look at another example of this, which is in the same spirit, but it works slightly differently than auto research and optimizes a slightly different thing. So I want to look at this paper called Meta Harness, which does something like auto research for model harnesses. So what is a harness to start with? A harness is basically just, we used to call it scaffolding. All the logic you put around a model to agentify it and make it do some kind of a task. The most popular example today, of course, is Claude Code. Claude Code is a harness around the base Anthropic Claude models. And what is the job of a harness? The job of a harness is to run some kind of reasoning, planning, tool use loop on top of a model to accomplish a certain task. Now, in the case of Claude Code, that task is pretty general and open-ended. The set of tools it has is pretty general. But you can construct model harnesses for more specific tasks, like, say, classifying text or something more specific than just a coding agent. And that is what this paper looks at. So this paper is saying that if you have a specific task for which you want to construct a harness around the model, you can automatically construct that harness by looping over an auto research kind of loop. And the way it works is very simple. And if you've ever done any kind of benchmark maxing, this is exactly what a human would do. So say you have a harness that you want to construct for some kind of a task. The overall system breaks into two big components. One is what they're calling a proposer, and a proposer is the agent which creates a new harness based on all the previous harnesses and their outputs. The evaluator is the second component, and the job of the evaluator is much simpler. All that the evaluator is doing is taking the harness built by the proposer and running some kind of benchmark on it. But very importantly, it's saving not just the harness itself, but all the traces that you get when running the benchmark on the proposed harness. And then all this stuff, the simplicity of this is really nice. All this stuff, the harness, the output of the evaluator, all these reasoning traces, this is simply stored in a file system. These are just directories and files in your local file system. There's no complex coordination mechanism. And then you loop back. So you get reasoning traces from one evaluation run of a harness, and it goes back to the proposer. So the proposer in this scheme is doing all the heavy lifting. In fact, as you can tell from this logo, they're simply using Claude Code as their proposer. And over time, what you have is many possible harnesses built by the proposer, along with their evaluation on a benchmark. And this proposer is free to look at all these previous harnesses and their evaluations and their tracing logs, and it can reason over all those traces and see what failed, why it failed, and it can use all that information to create a new harness. Now, the cool claim in this paper is that there's no special purpose logic to do that. If you have a powerful enough agent, in this case, Claude Code, you don't need to give it any special purpose logic. If you just give it a high level goal to optimize, you tell it that, this is the benchmark, this is the task you're trying to maximize. It is smart enough, or the underlying model is smart enough, and it has all the tools to go and do agenting search over your file system. So it can do ls, find, grep, read files, write files. So it is smart enough to go look in all these folders from older harnesses and their reasoning traces and do some kind of failure analysis. And then based on all that, propose a new harness that maybe tries to fix some of the issues with older harnesses. And they ran this on several tasks, one of which was test classification. And as you can see from this graph, doing this meta harness loop ended up with a harness that beat out all the handcrafted harnesses. So this is very bitter lesson pilled, which is that if you just throw search and compute at a problem, you'll come out with a better solution than some kind of bespoke handcrafted solution. There's one very important difference between MetaHarness and AutoResearch, which is that AutoResearch doesn't look at the code of all its previous attempts. It's only running experiments on the last good training Python program. And the only signal it's looking at is that one metric for the performance of the model. Whereas here, it's looking not just at the evaluation score on a task or on a benchmark, it's looking at a much richer set of data. So it's looking at the proposed code for the harness, all the reasoning traces. So this meta harness loop has much more information to improve its output with. And this really resonates for me because I had some personal experience with this kind of work, except I did it manually. So I recently designed and open sourced a harness specifically for automating standard operating procedures into agents. And I was trying to benchmax on SOP-Bench. And this is kind of exactly the loop I followed, but I did it manually in that I would run Proceda on this benchmark. I would see what the score is. I would look at the traces, or rather, I would ask Claude Code to look at the traces and do some kind of failure analysis. And then based on the failure analysis, I would improve my Proceda harness. And doing this kind of loop benchmaxing, it let me get Soda on SOP-Bench, but I was essentially doing by hand as a human this loop that meta harness just completely automates. And in fact, I was thinking at the end of all this, I spent a few days benchmaxing. At the end of this, I really was kicking myself for not doing this in some kind of auto research loop, which is what meta harness does. So again, it all comes back to this. If you look at, I think, the main thrust of the entire agent field right now, what all the labs and startups and everyone is focused on, is how do you just get humans out of the loop? How do you get the agents to rip on their own? And things like AutoResearch, meta harness are illustrations of how to do that. All right, I hope you enjoyed that. If you like content like this, consider subscribing, like the video, and I will see you next time.